What if the fundamental laws of physics aren't really laws? What if they're more like lines of code? And just like any software, what if that code has bugs? This might sound like science fiction, but it's a question being taken seriously in the highest circles of theoretical physics. Some of the most bizarre phenomena in our cosmos are starting to look less like cosmic mysteries and more like cosmic glitches. What if the universe is trying to tell us something about its own nature? And what if scientists have started to find the error messages? This isn't a story from a movie. This is about a very real, very strange idea that has hooked scientists and philosophers, the simulation hypothesis. The theory says that our entire reality, everything you see, feel, and know, is actually an incredibly advanced computer simulation. It's an idea that completely reframes the human experience, but it's always been just that, an idea, a philosophical what if, until now. Physicists are starting to look at the universe in a new light. They're treating its strangest anomalies and paradoxes not as problems with our theories, but as potential evidence. They're becoming, in a way, bug reporters for reality itself. They are filing reports on the glitches in the matrix, and the evidence they're finding is both fascinating and a little unsettling. So today we're going through the official bug reports, the strange clues that suggest our world isn't what it seems. The first bug report is about the most famous constant in physics, the speed of light. Nothing in the universe can travel faster than 299,792,458 meters per second. We've always been told this is a fundamental limit, a cosmic speed barrier. But what if we've been looking at it all wrong? In any computer simulation, especially one as huge as a universe, the biggest challenge is processing power. Every calculation, every interaction takes up resources. A simulation on this scale would have to be optimized, and one of the best ways to do that is to set a hard limit on how fast anything, including information, can travel. Think of it like the refresh rate on your screen or the processor in a video game. There's a maximum speed at which the system can update what's happening. The speed of light, seen this way, starts to look less like a law and more like a system spec. It's the ultimate processing speed of the cosmic computer running our reality. It's possible the huge distances between stars aren't just a feature of space, but a clever way to manage system resources, preventing any one part of the simulation from having to render too much detail at once. The universe has a speed limit, and it might just be the first clue that we're all running on the same server. The second bug report takes us into the weird world of quantum mechanics, and an experiment that has baffled scientists for over a century, the double-slit experiment. It's simple. You shoot tiny particles, like electrons, at a screen with two slits in it. Logically, the electrons should go through one slit or the other, making two lines on the detector behind it. But that's not what happens. Instead, the electrons act like waves, creating a complex interference pattern, as if each particle went through slits at the same time. And here's where the glitch really shows up. If you put a detector by the slits to see which one the electron goes through, the wave pattern disappears. The very act of observing it forces the particle to pick a path, and it goes back to acting like a normal particle, creating the two lines we expected all along. Supporters of the simulation hypothesis see this as a huge piece of evidence. They argue it's a form of computational shortcut. The simulation doesn't bother rendering a definite state for a particle until it has to, that is, until it's observed. It's the ultimate optimization trick. Why waste processing power calculating the exact state of every particle when you can just leave them as a wave of possibilities? Only when a measurement is made does the system render a specific result. It's like a video game that only renders the details right in front of the player to save memory. In fact, former NASA physicist Thomas Campbell is designing experiments based on this idea, proposing that if information about an event isn't recorded, it's as if the event never truly happened, suggesting a reality that only becomes solid when we interact with it. Our third bug report is what Albert Einstein famously called spooky action at a distance. It's a phenomenon known as quantum entanglement, and it might be the most profound glitch of all. When two particles become entangled, their fates are linked, no matter how far apart they are. If you measure a property of one particle, like its spin, you instantly know the spin of its partner, even if that partner is on the other side of the galaxy. This instantaneous connection seems to break the cosmic speed limit we just talked about. Information appears to travel faster than light, which should be impossible. But in a simulation, this spookiness has a logical explanation. The system doesn't need to send a signal between the two particles at all. Think of it like this. In programming, Instead of creating two separate objects that have to talk to each other, you can just create two pointers that both refer to the same piece of data. Change the data using one pointer, and the other one reflects that change instantly because they're both looking at the exact same thing. Entangled particles might not be two separate things communicating faster than light, but rather a single entity whose properties are stored in one place in the system's code. The distance between them doesn't matter because, to the processor, they're right next to each other on the hard drive of reality. It's a system shortcut, a bug that reveals the architecture of the program. These individual bug reports are interesting on their own, but when you look at them together, they point to a single, mind-bending idea. This brings us to the work of philosopher Nick Bostrom, who in 2003 laid out the modern simulation argument. Bostrom created a trilemma that forces us to face some uncomfortable possibilities. He argues that one of the following three things must be true. 1. Civilizations like ours almost always go extinct before they can run super advanced ancestor simulations. 2. The advanced civilizations that survive simply have no interest in running them. Or 3. We are almost certainly living inside a computer simulation. Given how fast our own computing power is growing, the idea that we might one day simulate consciousness seems more and more possible. If that's true, and if even a small number of advanced civilizations decide to run simulations of their past, then the number of simulated realities would eventually be far, far greater than the one base reality. Statistically, it would be overwhelmingly likely that we are in one of the simulations, not the original. This idea is now being explored through a new lens, information theory. Physicist Melvin Vopson has proposed what he calls the second law of infodynamics. He argues that in any system, information entropy, basically the amount of disorder in information, tends to decrease over time. This is the exact opposite of the second law of thermodynamics, where physical disorder always increases. Vopson suggests this universal drive toward information compression is a law of nature, visible in everything from how electrons arrange themselves in an atom to genetic mutations. He claims a universe as complex as ours would need built-in data optimization to run, and that's exactly what he thinks we're seeing. This even led him to propose that gravity might not be a fundamental force, but something that emerges from the universe trying to minimize its information content, just like a computer compressing a file. So are these real glitches in the matrix? Are they proof that our reality is written in code? Or are they just the limits of what we currently understand? Paradoxes that a future, better theory of physics will solve. This is where we have to be careful. The biggest criticism of the simulation hypothesis is that it might be impossible to prove wrong. Any evidence we find to disprove it could, in theory, just be part of the simulation, designed to keep us in the dark. Some physicists also argue that simulating our quantum reality is mathematically impossible with the kinds of computers we can imagine, suggesting the universe is way too complex to be a simulation. We're left in a state of deep uncertainty. The bug reports are in, but the programmers, if they're out there, aren't talking. The clues are scattered through the cosmos, from the speed of a photon to the swirl of a distant galaxy, and they challenge our most basic ideas of what's real. If we are living in a simulation, then the great questions of existence suddenly have a technological spin. Who wrote the code? What's the point of the program? And the biggest question of all, what, if anything, is outside the simulation? We don't have the answers, but for the first time in history, we're learning how to ask the right questions. The universe is full of glitches, and we're just now, finally, beginning to notice. These cosmic glitches, from the speed of light to the bizarre rules of the quantum world, are painting a strange new picture of our universe. If you find these mysteries as fascinating as we do, leave a comment letting us know your thoughts. Make sure to subscribe and turn on notifications because you never know what we are going to explore next.